Is my screen visible, sir? Is my screen visible?
Yes, sir. Yes,
Okay.
yes, sir.
Okay, thank you.
It
Thank
is
you.
visible.
So I welcome you all for this QT-03 basics quantum programming. So in this series, today we're going to cover about implementing algorithms on cloud-based quantum computer. So today we're going to compare simulations, and tomorrow Ms. Janani going to take about how to run in real system. So that is the idea. So I want to thank Ms. Geetanjali Venkatraman. She is working as a thought work illustrator in UK. So she created this material, whatever I'm showing in this PPT, it is a PDF. Okay, I gave that link also. So if you have time, please go and watch that PDF. So I requested her permission to make that PDF into animated PPT. So whatever, if you are looking this work, is everything is handmade. Okay, it is like a cartoon based material. So I really thank her for his generosity. So today's topic is quite interesting. Whatever you learned so far, okay, whatever we learned, gates, whatever you gain, circuits, Qiskit, penny lane, Java string package, everything we need to work for quantum algorithm. So this is our ultimate ambition. Okay. So whatever the classical algorithm we are working, classical knowledge we have, we need to convert into quantum. So that is the main purpose. So this is a conceptual model. So whatever the quantum algorithm we are discussing, it is a conceptual model. You can make it as reality step by step. All your hardware, software will take care. No need to bother about. You no need to know exact physics how it is working. Okay, even from computers and IT background, you are able to write a program for quantum computing. So we will recap what is a quantum algorithm. So quantum algorithm is made up of so many signals. So we are playing with qubits. So more and more qubits, more and more signal going to interfere. So all these signals going to collapse at some point. Okay. A quantum algorithm uses a global property of the values in the qubits to change their amplitude. So we'll use that global property to change value. So this is the key concept in quantum algorithm, and we'll see which gates will help you to change global property. So there are two goals while writing a quantum algorithm. We need to reduce amplitude of wrong answer, then we need to increase amplitude of correct answer. So if you are running any quantum algorithm or any quantum process, it will give a mixed result. It is not like classical computer. It is not like deterministic output. The output always varies. Okay, so it will give some correct answer, it will give some wrong answer. So we need to be very careful about which one is correct, which one is wrong. So that is the whole agenda of quantum algorithm. So when you can say which one is correct, which one is wrong, you need to make a measurement. Okay? We already covered whenever a measurement is made, there is a high probability the superposition will get collapsed and you will get the answer in correct form. Okay? So only during the measurement, you are able to know which one is correct, which one is wrong. So how do quantum algorithm works? In contrast to classical algorithm, there are only few quantum algorithms are there. So our learning will be very narrow down when compared to classical. Very few quantum algorithms are there. They appear to be capable of solving harder problem in faster way. So this is the whole theme of quantum. So whenever if you have a harder problem, then only go for quantum. If your problem is solvable by your classical computer, don't go for quantum. So it is waste of time. So these algorithms are composed and executed very differently from what we are used to in classical computing. The way we are thinking about the algorithm, the way we're going to apply that algorithm in quantum system is entirely different. So whatever you learned in classical, you need to unlearn in this phase. So this is my okay. So quantum algorithm will work better on the problem with certain structure to provide the speed up. Okay. So the first such algorithm is demonstrator is called Bessartain-Vaziriani algorithm. So if time permits, we're going to cover this algorithm. To understand them a bit better, we need to look bit closely to working of three important algorithms: Deutsch-Jozsa algorithm, Grover's algorithm, Star's algorithm, and variety of algorithms are there. You can look up with this quantum algorithm .zoo.org. So if you go to this website, you can see n number of algorithms available in quantum domain. But when compared to classical, it is very small subset. So before dwelling into quantum algorithms, we need to understand what is the measurement, what is the superposition, and what happens to each and every gate operation. So it is like a quick recap. We'll go from the basics in order to understand the better foundation for quantum algorithms. So take an example of qubit. Qubit exists in superposition. It will go anywhere in between 0 and 1. Okay. So if you want to map a qubit operation in a graphical format, it will go like a circle. So qubit, if you want to trace that motion of an electron inside that between 0 and 1, it will form a path. Okay. So it is like a signal, periodic signal. So the path it really trace is looking like a wave, appear like a wave. So this is the physical meaning. And each and every wave contains amplitude. Their amplitude will determine signal strength of particular state 0 or 1. Imagine the entire positive circle related to state 0, the entire negative phase related to state 1. So this is how we're going to map the movement of a qubit in a graphical form, right? So its amplitude determines the probability of the outcome. So whenever if you want to know what is the outcome, what you need to do, you need to measure that signal. If you measure, the measurement signal will come from amplitude, right? Superposition is stateless position. The superposition is not stateless, it is state. It is combination of state. So you can say it is a mixed state. You cannot say it is a stateless, it is a mixed state. So whenever if you want to measure a qubit, so according to the location, it will lead either 0 or 1. Okay. So this will give the higher probability of chance, the more likely to get the outcome according to the location of your qubit. Okay. So if you want to depict the entire qubit motion to a clock, so take an example. This is a clock. Okay. So replace this clock, all this number with how far away from they are from horizontal axis. So what could be the horizontal axis? 9 to 3. So draw a line. So this line will act like x-axis. Maybe I will use a highlighter or pointer. So look at here. Uh, uh, 2 o'clock is 1 unit away from 3. So that is why you replace 2 with 1. And 1 o'clock is 2 unit away from 3. So that is why you replaced 1 with 2. So based upon the position, based upon your x-axis, you mention how much unit it is far away. So look at downside. Okay, 4 is away from 3. If you measure, it will come to definite position. That is the meaning. If you measure qubit, either it will come to 1 or 0. Pure state are called definite position. Right? So from 3 to 4, it will take 1 unit, but with respect to positive, the upper hemicycle, okay, the lower hemicycle is you need to represent minus value. Right? So we need to show some difference, okay, from x-axis. So replace all this value and try to plot in XY graph, okay, plot how far they are away from 0 hour and travels from 12. So imagine, make a mention of 12 o'clock. So what is the value of 12 o'clock? 3. So how far it is from 0? Okay, you need to map each and everything with XY plot. So y-axis mentioned for how far it is from x-axis, and x-axis mentioned hour. Okay. So take an example of 1 o'clock. So what is the position of 1 o'clock? 2 units, right? So 12 o'clock means 3 o'clock means 0. So likewise, you try to point, you try to map all these clock position and you will get a waveform. So this is like periodic. Okay, your clock will act like periodic in the same way your qubit motion will act like periodic. So it is traceable. So whenever if you want to look at a signal, okay, this entire length is called wavelength. Right? We will refresh from top to another top peak. Okay, so it will act like a period, a complete cycle of a wave. Okay, the signal strength with respect to y-axis is called amplitude. So this is the reference how strong that signal is relevant to x or y. Suppose if you are adding two signals which is in same phase, okay, if you are adding two signals, okay, then what you will get, the resultant wave have the higher amplitude. So here amplification will happen, increase in the amplitude. Suppose if you are taking the two different signals, okay, if you try to add, what you will get, it will nullify each other, because opposite signal of equal strength. So each and every time if signals are get interpolated or interference happen, okay, so it will be used to cancel wrong answer, it will be used to amplify correct answer. So this is the whole idea about quantum. So when you run any quantum algorithm or any quantum experiment, you'll get mixed kind of result, not only the perfect exact correct output. So you will get correct output as well as you will get wrong output. Okay. So what is the chance of getting correct answer with higher probability? So this is will happen only after measurement. So when you do measurement, what happens? Amplitude will becomes into probability. So when you do measurement, so refresh from previous topics. When you do measurement, okay, it will appear like a particle. So until it is in quantum state. So this is the difference. Okay. So whenever if you do measurement, it forces qubit to make a decision like a defined state. Either it will go to 0, either it will go to 1. Okay. It will lose the superposition. And if you want to describe a state and position, you need to do measurement. So this entire what you can say, this path represents qubit acceleration, but here we're going to do measurement. So before this you have multiple states, but after this you will have only binary state. So each and every time you will get random answer, depends on the probability, how close it is to the basis state. So you can say the random answer is no good in classical, but in quantum it is very, very good. Okay. So however, a quantum computer can be coaxed into more likely answer, more random answer. Okay. So each and every qubit have two potential outcomes. So take an example of either 0 or 1 when you do measurement. Okay. So each outcome has an amplitude. So take an example of only one qubit. So one qubit have two different probabilities, two different amplitudes. So for positive state, stage 0 alpha is the amplitude. For state 1 beta is the amplitude. Okay. So before doing measurement, it is in superposition. If you have two qubits, so you have four possible combinations. Okay, we already covered. But when you do measurement, two qubits will lead to four outcome. Four outcome will translate it into four amplitude. Okay. So amplitudes can be controlled by rules. So this is where we are putting quantum gates. So each and every time what we try to do, we need to increase the amplitude of correct answer. Okay. So each and every time the interference will happen if you do a quantum operation and we want to cancel out the unwanted one, like a noise cancellation headset, right? So this is the whole purpose of quantum algorithm. In quantum algorithm, what we'll do, we'll increase the correct amplitude, we will try to reduce the wrong amplitude. So generally, a likely correct answer, you need to write an algorithm, quantum algorithm. The algorithm is made up of gates, rules, okay, which will manipulate amplitudes of qubits. So each and every time if you do a gate operation, what it will do, it will bring changes in your qubit, changes with respect to amplitude. Okay, so each and every time it will get interference. Okay, so amplitudes of wrong answer will cancel each other, and amplitudes of right answer will add up and amplify. Okay, you need to do multiple times. So this is the problem in quantum. So in classical, if you are running a program single time, you'll get result. But in quantum, you need to run multiple times. Then only you are supposed to do measurement. When you do measurement, you will find undecided outcomes less probably, correct answers more likely. So it is like a magic. Right? So we'll cover up the gates. We'll cover up the gates quickly. In classical, we'll have electronic gates. We will explain. We will see during explanation. Wait for some time. Okay. So all these gates will contain one or two statements and are examined at each and every gate. Okay. Whenever the statement passes, depends upon the roots of the gate. Okay, you will get the output. Not gates are not used to provide superposition. The Hadamard gate will create equal superposition. The remaining gates, it will try to modify the superposition state. We'll cover, please wait. Okay. So take an example of AND gate. So AND gate have two inputs, and these two inputs will converted into one output. So if both statements are true, then only you will get output. Take an example of OR gate, which is exactly opposite of AND. Okay. If one of the input is true, then you will get true output. Take an example of NOT gate, which is complementary for both AND and OR. Okay. So whenever if you give true, your output will be false. Whenever if you are giving false, your output will be true. So it will negotiate opposite of the given statement. Okay. So each and every quantum logic gates will obey rules in algorithm. These rules are called gates. Okay. So the gates are applied to one or more qubits at a time. So there are single qubit gates, multiple qubit gates. So according to your need, you need to select your gates. Okay. The gates make qubits move around the block sphere. So each and every time when you implement any gate, it will change superposition state. This changes amplitude of each outcome of the qubit. Okay. So we'll see this important 4 gates. Take an example of NOT gate, X gate. So imagine your qubit lies in state 0, pure state. When you implement NOT gate to state 0, you'll get state 1. Okay. So this is what it happens. When you implement a NOT gate in stage 0, it will move to state 1. When you apply NOT gate to state 1, again it will move to state 0. What happens if you apply a NOT gate in superposition? So this is for pure states. So right side, we need to do for a superposition state. If you apply a superposition qubit state to a NOT gate operation, it will interchange this probability value. So look at here. So alpha stage 0 plus beta 1. Now it is converted into beta stage 0 plus alpha state. So it will interchange the probability. So you need to remember this. So if you are looking at 2D, it will do rotation in 45-degree axis. It will do rotation in 45-degree axis. So this is the operation of NOT gate. So if it is in 3D, it will do 180-degree. Phase flip, which is equivalent to rotation in unitary axis. Sorry, what you can say. Phase flip, it will rotate only phase of that signal. phase of the signal. This slide, it is about NOT gate, block sphere. I will explain. I will try to explain after these gates in 3D. So wait for some time. So phase, it will change from plus to minus or minus to plus. So it will only operate in state 1. It will not operate in state 0. So that is why you can see changes in state 1, right? So if you apply Z gate in state 0, it will remain as it is. But if you apply Z gate in state 1, it will apply a phase shift minus 1. Again, if you are applying Z gate in minus 1, it will flip to state 1. So it will go from minus to plus. So in 0, it won't do anything. So this is in pure state. So if you are looking at left side in superposition, what happens? What happens? Okay. So this is the superposition. It will change the sign of the second qubit, second state. So look at this. So this is the positive phase. This is the negative phase. So because of changing the phase, it will introduce a negative sign in second state. So it will do 45-degree half circle rotation, okay, around stage 0. I will share this slide. Please go through it. If you are applying Hadamard gate, what happens? If you are applying Hadamard gate from stage 0, it will go to positive state. Okay, it is in equal superposition. If you are applying state 1, sorry, Hadamard in state 1, it will go to negative state. So plus and minus are at 90-degree. So this is orthogonality. So positive state and negative state are 90-degree in 2-dimensional. Okay, so remember. Suppose if you are applying Hadamard in superposition, then it will create new superposition. So this is very interesting, right? So if a qubit is already in superposition, if we apply Hadamard gate, it will create new superposition. Yes, exactly. So this will create 22.5-degree changes from 0 to plus or 1 to minus. So if you do Hadamard twice, it will go back to original state. So it will do in between, okay, plus and minus around the stage 0. So take an example of CNOT gate, control gate acts on 2 qubits. Okay, X gate, Y gate, Z gate or single qubit gate, where CNOT gate is 2 qubit gate. So it will flip the second qubit if the first qubit is 1. So try to understand the CNOT gate, which is very important. Okay, so we have 2 qubits. We have 2 qubits. Q1 will act like control. Q2 will act like target. Okay, so after going through this control knot, the state will get changed. That is why we mentioned Q1 dash and Q2 dash to change, to notify changes in your state. Whether it is acting or not, you need to represent mathematically at least, right? So take an example of Q1 and Q2. So apply 0, stage 0. What I do, I try to write. So stage 0 for Q1, stage 0 for Q2. So 0 means nothing will happen. So nothing will pass. So this NOT gate is not activated. So 0 will retain as it is. So that is why the output is 0, 0. So apply 0, 1. So Q0 is Q1 is 0, Q2 is 1. So 0 means nothing. Okay, nothing will happen. It is not activated. 0 means the state will retain as it is, 0, 1. So Q1 is 1 and Q2 is 0. Now what happens? Power supply will be there. Okay, it will come down. It will come down. Okay, it will activate NOT gate. This 0 is converted into state 1. So always mention state. Please always mention state. So 1 means 1. So what it means, whenever Q1 is 1, it will flip Q2. So flip will happen in Q2. Are you able to get the idea? So this is the logic. So control knot used to create entangled qubits. If we want to create an entanglement, then we need to have CNOT gate. So I will skip this entanglement part because we already covered so many entanglements. Let's dwell into algorithm. Okay. The first algorithm we are about to cover is Deutsch-Jozsa algorithm. Deutsch-Jozsa algorithm. So what is the problem we're going to tackle in Deutsch-Jozsa? Okay. The problem is, who am I? So we need to decide who am I. So it is related to mathematical terms. Okay. Suppose if a function is given, I am a function. Okay, f of x. Okay. My input could be either 0 or 1. My output could be either 0 or 1. So binary input is given, binary output will get produced. Okay. So based upon this, based upon your input and output combination, you need to decide whether your function is constant or balanced. So let me explain what is a constant and what is a balanced. Okay. Suppose if your function f of x, I try to point out. Suppose if your function f of x always produce 0, then you can declare the given function is constant. Okay. So if your given function f of x always yielding 1 constant output, then you can decide your given function is constant. On contrast, if f of x equal to x in a single run, next time if you are giving the same input, it will negotiate the output of the previous outcome. Then you can decide it is a balanced function. So the difference is very simple. So in classical, how we need to approach? Suppose if you are giving f of 0, it will yield 0. Suppose if you are giving f of 1, it will yield 0. Then what you can say, so if you are running twice, then what you can say, this function is constant. You can decide. Suppose if you are giving f of 0 equal to 1, the next time you are changing the input f of 1 equal to 1, the output remains same, then it is also a constant function. Are you able to follow this slide? Am I audible? Are you able to follow? Is it clear? Great. Thank you. Thank you. So look at left side. If you are giving f of 0 and you are getting 0 and you are changing your input f of 1, the output is 1. Each time the output varies, negotiates. Otherwise, if you are giving f of 0, the output is 1. If you are giving f of 1, the output is 0. Again, the output varies. Okay, for this also it varies, for this also it varies. Then you can decide the given function is balanced. So this is the logic. So in classical, you need to run the function twice to decide whether it is constant or balanced. So understanding problem is very important. So that is why I gave step-by-step explanation. I hope everybody able to follow. Okay. Suppose if you want to implement in quantum we'll use oracle. So like a predictor. In religious predictor, each and every structure have this person. Okay. So this oracle will predict a given function is constant or balanced in a single run. So this is the beauty of quantum algorithm. So in classical, we need to run twice at least. In quantum, in just one single query, able to decide the given function is constant or variable. So this is proposed by David Joyce in 1990. Okay, in 1985 he proposed quantum Turing theory. Okay, in Oxford. Okay, so he gave the template for the very first quantum algorithm with very good mathematical abstraction. So how quantum becomes so much of popular? Because of theoretical proof. Theoretically they prove they are better than classical counterpart. So we'll discuss about Deutsch-Jozsa algorithm. Okay, two qubits are there, x equal to state 0, y equal to state 1. So we have two qubits. We are assigning the different value. So the first qubit is for computational purpose. The second qubit is for auxiliary purpose. So second qubit they always say ancilla qubit. They always say ancilla qubit. So we are implementing Hadamard for first qubit, then Hadamard for second qubit also parallelly. Okay, we are going to give a function. This function is a black box. You don't know what type of function. You need to determine what type of function based upon this architecture. Okay, what Hadamard gate will do? Can anybody say what Hadamard gate will do? Can anybody say what Hadamard gate will do? Exactly. It will create equal superposition. So you need to mention the word equal superposition. Okay. So from state 0, if you are applying Hadamard gate, okay, actually you need to represent mathematically in this way. If you are applying Hadamard gate to stage 0, which will give positive state. So here we'll get positive state. Okay. From state 1, if you are applying Hadamard, which will yield to negative state. Here you will get negative state. Are you able to observe? Because we have different initialization for two different qubits. Yes. Again, what we are doing, we are implementing Hadamard out of this function. So we don't know what type of function it is. We don't know what type of function given. Okay. So our input positive state and negative state going to interfere with this function, and this will give some output. Okay. This output going to react with your Hadamard gate, and this Hadamard gate will yield either 0 or 1. So this is the logic. We don't know what type of function is given, okay, but we know what is the state before that function, right? So then what we need to do in quantum, we need to do measurement. So the input qubit is x equal to 0, the helper qubit y equal to 0, which is ancilla. You can say ancilla qubit. It is helper. So this qubit is ancilla. You can say supportive qubit. Yes, we need to have more than one data, but actual data is this one. This is the single output. So this is for single qubit example. Imagine like this. Okay. So each qubit will go through your Hadamard gate. Each qubit will go through Hadamard gate, it will set them in equal superposition. So you don't say just superposition. Whenever if you are looking at Hadamard gate, always it will create equal superposition. So what is the logic? The oracle function f returns 0 if it is constant. F returns 1 if it is balanced. So based upon your output, you can decide in single measurement and you can reveal whether the given function is constant or balanced. Are you able to get the idea? So please go through this. If you have any question, you can ask. Right. See, we have two qubits, stage 0 and state 1, and we are applying the stage 0 for Hadamard. It will yield positive state. And we have state 1, we are applying Hadamard gate, which will yield negative state. So these two are different inputs for your function. You don't know what function it is. Suppose if your function is constant, what happens? It will yield positive state. Okay. From positive state, if you are applying Hadamard, what happens? From positive state, if you are applying Hadamard, what you will get? Can anybody answer? No? 0. State 0. Okay. Suppose if your function is balanced, then it will produce negative state. From negative state, if you are applying Hadamard, okay, it will yield to state 1. Okay. So after measurement, you'll get values. Either 0 or 1. So before this you have quantum state. So after measurement, you have classical value. So this is the difference. Fine. So try to implement oracle. So we have 4 options: f of x equal to 0, f of x equal to 1, f of x equal to x, f of x equal to not x. So we covered 4 options, right? So let's say function outputs, you'll get 2 outputs, state x and y XOR with f of x. Yes, y we need to always equal to 1 because we need to contradict your input option. That is why. If x is state 0, y should be state 1. We need to differentiate. Okay, thank you. Okay, so where this modulus operation is XOR operation. Okay, take an example of case 1, f of x equal to 0. So make a truth table xy, y XOR with f of x. Okay, 0, 1, what will happen? So 0 XOR 0 XOR with 1. What will do? 0 XOR with 1. What will get out? 1. Because XOR will give any difference between your input. If there is any difference, yes, 0 is different from 1. So that is why you got out. So XOR used to give, XOR used to identify whether given input, are same or not. Same or not. So same means 0. Okay. Different means it will produce 1. So remember this logic, very simple. Okay. So 1 1, if you do XOR 1 1, it will give 1. Right. So likewise it will do. So here I did with x, but what we need to do? We need to do with y. we need to do with y. So let's see first combination. So what is given? Y. Y is given. What is f of x? F of x equal to 0. So 1 XOR with 0. What will you get? 1. Okay. So next combination. Y is 1. Okay. What is f of x? F of x is 0. So f of x is always 0. So 1. So this is the logic. All of you able to get the first case? Very simple. Okay. So if you visualize circuit, x written as it is, and the second output always y XOR with f of x. Okay. So this is how it looks like mathematically. Okay. Second case, f of x equal to 1. So substitute all these values. So what is the function given? Y XOR with f of x. So take this input. So 1 XOR with f of x. 1, 0. Inputs are same. Inputs are same. So do like this for all combination and you'll get output. Now look carefully. Whatever the output you got in case 1 is totally opposite to case 2. So what it means, if you are visualizing like a circuit, okay, if you put not operation of output, you will get output of case 2. So apply not operation of this output, not operation. So not of 1 is 0, not of 1 is 0, not of 0 is 1, not of 0 is 1. Are you able to get the logic? So output is state x, not state y. Okay. So case 3 is balanced f of x equal to x. So what it means, whatever the value of x, you going to do XOR with y. It is very straightforward. So 0 XOR with 1 leads to 1. Okay. So 1 XOR with 1 leads to 0. So 0 XOR with 0 gives 0. 1 XOR with 0 is 1. So if you visualize circuit, it will look like control knot. It will look like control knot. So what is the logic of control knot? If there is input in x, if there is input in x, so this is the case, input is 1. Okay, then what it will do? It will bit flip y. Are you able to get the logic? So whenever the input of x is 1, it will do bit flip of y. Otherwise, it will retain as it is. Okay, so this will act like y XOR f of x like a CNOT. Case 4 balanced f of x equal to not x. So what it means, you create x dash, you create x dash or x bar. Okay. So what is the input of x? 0. You do negotiation 1. Okay. So y, what is the value of y? 1. What is the value of y? 1. XOR of f of x. What is the f of x? 0. But what is the not x? 1. So 1 XOR 1, you will get 0. Are you able to get the logic? So do like that. Do like that for remaining cases. Remaining cases, you will get the output exactly opposite to this. Exactly opposite to this. So if you put NOT gate for your case 3 output, you will get output of case 4. So here 1 means here 0. Here 0, 0 means here 1, 1. So here 1 means here 0. What it means, all 4 possible cases are entirely unique or entirely different. If you are looking at the output, you are able to differentiate. So if you are able to differentiate, it is reversible. So this is the key point in quantum. So how many inputs are giving the same number of output you need to maintain. So that is why we are seeking one extra input for your operation. Okay. So this is an example for reverse CNOT. So this is the mathematical detail of Deutsch-Jozsa, right? We are applying. So after 2 Hadamard gates, what will happen? So XY will tend to a tensor product, right? So I won't explain. We are running out of time. Do at your leisure time. I will share this material. Okay. So each and every qubit will tensor, get multiplied, and this is the combined state, right? When you pass through the function x comma y XOR with f of x, you'll get state 0 0 XOR with f of 0 plus state 1 0 XOR with f of 1 minus 0 1 XOR with f of 0 minus 1 1 XOR with f of 1. So if we do for whole probability, it is divided into 1 by 2. Okay, this is the output when you pass the whole function. So this is the output. This is the output state we will get after this function. Okay, so let's do mathematically. F of 0, we are combining two states, f of 0 and also f of 1 always gives 0. So this is the tensor product, and taking the common term state 0 out of this, and you have common terms. Okay, so the first one for first qubit, the second term for second qubit, and combine two functions, constant f of 0 and f of 1 equal to 1. And if you are taking the common terms, you will get this combination. So what is the difference between these two terminology? Plus and minus. So everything remains same, right? For balanced, you do the same and pull out the common term, you will get minus 1 as the common term, and do for f of 0 equal to 1, f of 1 equal to 0, and the common term is minus. So what is the difference? So here minus 1, here just minus, and everything remains same. So this is the given circuit. This is the given circuit. Okay, this is the common term we got after this function. Okay, so this will becomes into two factors. One is for constant function, one is for balanced function. So look at this constant function. This is the tensor product term, right? So if qubit 1 is in state plus, if qubit 1, so this is qubit 1, this is qubit 1, the output is in state plus. Suppose if the function is constant, what it will produce? It will produce positive state in first qubit after this function. Okay, so if you apply Hadamard to this positive state, it will go to state 0. It will go to state 0. It cannot mention 0. Imagine this is state 0. Okay, then what you are doing? You are doing for balanced function. Suppose if your function is balanced, try to change color. Suppose if your function is balanced, then what this function will produce? It will produce minus state. So if you produce minus state, if you apply Hadamard gate, it will produce state 1. Okay. Suppose if you are doing measurement, you'll get 0 as output for constant function. Okay. 1 as output for balance function. All of you able to understand? What I do, I try to show codes of Deutsch-Jozsa. I try to show code of Deutsch-Jozsa. I'll copy this code. I try to put in chat box. So copy this code and try to execute. I try to zoom this code as well as put in line number. Okay. So these 4 lines are to import all your libraries and packages. So line number 7, what we are doing, we are creating a quantum circuit. We are creating 3 qubits and we are creating 3 classical bits. Okay. And suppose if you want to implement the constant function, you need to maintain h of 0, x of 1, right? It is up to you how you want to maintain, right? So next we going to implement h of 1 and control not 1 comma 2, and we are applying a barrier, and this is the whole circuit, right? Then we are doing measurement. Again we are applying barrier. We try to print that circuit. So this is the whole architecture of your Deutsch-Jozsa algorithm. This is the whole architecture of your Deutsch-Jozsa algorithm. So what we are doing, we are creating a Hadamard gate in Q1 and we have control knot from Q1 to Q2. Same way, we are applying a control knot from Q1 to Q0. So what it means, it will create entanglement between 3 qubits. So Q1 is control, Q0 and Q2 will act like target. Are you able to understand? Any doubts? We need to measure. No, we need to have Hadamard gate in order to produce the output. So it will go back to original state, right? But here it will do phase kickback. So that is why we need to have measurement. I will try to explain. Suppose what I can do, I can take whiteboard, open board. Suppose if you have a qubit, okay, Q1. Suppose if you have a qubit Q1 and if you have Hadamard gate, right? So the starting state is stage 0. What happens if you apply Hadamard? What could be the output after Hadamard? Yes, state plus. So after Hadamard, it will create state plus. Suppose if you are applying Hadamard again, what you will get? Stage 0. Great. So when you do measurement right now, what you will get? Binary value 0. Same way. So if you have one second qubit Q2 and the starting state is plus, and if you are applying Hadamard gate, it will go to negative state. Again, if you are applying Hadamard gate, you will get state 1. When you do measurement, what you will get? You will get binary value 1. So this is why we require 2 Hadamard gates in order to get binary value. So we are mapping our output to binary value. If it is 0, constant, 1 means balance. Now you able to get why we are using 2 Hadamard? Great. Thank you. Suppose imagine you have control now. Okay. So normally this will act like control. This will act like target. Am I correct? Suppose if you have stage 0, here you have 0, you'll get 0, 0. Suppose if we have state 1, okay, if you have state 0, what will get? What will get at the output? 0, 1, but it will introduce a phase flip, which is a global change. So here you will get a minus change. So that is called phase kickback. So that is how our output is changed into positive state and negative state in Deutsch-Jozsa algorithm. So our function will react according to the opposite inputs. So that is why we are declaring opposite inputs. Are you able to get the idea now? So that is why we are declaring with different inputs. So next what you do? You try to measure the outcomes. So here we need to select the kernel. What I did, I used the previous version. Here is not defined. So if you are getting this problem, what you can do, go to environment, try to select this diskette version. Yes. Yes, sir. I will take 3 minutes break. Thank you.